So let's talk a little bit about the adjoint action of G on G. The adjoint is going to trade for us the mapping from the Lie group to a particular set of invertible linear transformations, basically on the Lie algebra. Although we're making a choice of basis, and so we're trading the Lie algebra for a copy of RD. But more generally speaking, a representation of a group on a vector space V is what? It's a subgroup of particular linear transformations on invertible linear transformations on V, which is homomorphic to the group. I mean, invertible, of course, because it's a group, right? So every element has an inverse, so it has to have what corresponds to it in the subgroup of linear transformations must also be invertible transformations, all right? Anyway, so that's a representation of a group. It's a version of the group, if you will, a shadow of the group, if you want, inside GLV. All right, so let's talk about lemma 8.9. Lemma 8.9, we have for all G and G and for all X and Y in the Lie algebra, the commutator of these adjoints is the adjoint of the commutator. So remember that the adjoint of G is the differential of the conjugation map at the identity. As the conjugation map goes from G to G is a group homomorphism, the differential is a Lie algebra homomorphism, hence this is the case. Or we could just calculate it. This and that is this and that, which is remember we proved that the Lie bracket is the commutator bracket, so I'm using that. And the G's cancel, but there's a leftover G and G inverse outside, and there you have it. So there's a simple little proof of that lemma 8.9. Now, so we should note that the adjoint, going from G to the general linear group D by D matrices over R is a smooth homomorphism, and this means that the adjoint sends one parameter groups in the Lie group to corresponding one parameter groups in the invertible D by D matrices over R. Definition: little, yet another adjoint, little at X, as a transformation from Lie algebra to Lie algebra for a fixed algebra element X. It's going to be the mapping that we like to. I mean, if you study Lie algebras from sort of a more axiomatic perspective, like say maybe, what is that book? Erdmann, was it? Anyway, there's lots of nice, somewhat axiomatic treatments of Lie algebras that have little to do with the group. And this is one of the things you like to play with, this adjoint mapping, where you basically freeze one of the bracket entries and let the other one be the variable. Anyway, this of course gives you a linear transformation because this is linear in the second slot, and X just sits there. So this is the little adjoint. It's just little adjoint of X of Y is bracket of XY. All right. Anyway, the little, like I said, the little adjoint is formed by fixing one of the slots in the commutator, or freezing it if you like. Proposition: for all X in the Lie algebra, the big adjoint of e to the X is the exponential of the little adjoint of X. Now here this is the exponential of a linear transformation, so this is understood as a series of composites of the linear transformation adjoint of X with itself. On the flip side, this is conjugation by the e to the X map. All right. Well, anyway, the notation is explained below. So here's the first thing to do is explain the notation in more details. So we fixed a basis beta for G, and the adjoint of X goes adjoint sub X goes from Lie algebra to its Lie algebra. This corresponds uniquely to some matrix A. So e to the A would be sum n equals 1 to infinity of a to the n over n factorial as usual. And so the left map and L sub EA goes from G to G, defines a linear transformation on G, which we denote exponential of add x. All right. I guess there's a question of basis dependence, but it's not basis dependence because of this identity error. All right, anyway, finally, words. Let's get to the point. The exponential of the little adjoint of x acting on y is, what that means is I plus this plus that's 1/2 that squared plus 1/3 that cubed, 1/3 factorial add x cubed acting on y, right? So when you actually work that out, what is it? That's nested commutators. It's commutators upon commutators upon commutators upon commutators upon, well, you get the idea. So like y, and then just a bracket of xy. The first one gives me bracket of xy, but then you feed it to add x again, so it's x bracket xy, and so forth and so forth. So that's the notation. That's what's meant by the exponential of the adjoint of x. So here's the proof of the proposition 8.10, which probably by now we forgot what we were trying to prove. We were trying to prove that this is equal to that. All right, so here's how. Prove. Now I guess I've got room for this thing too. For x in G, we have that the differential of the adjoint acting on I is an element of GLD. That's a matrix representing add x. That is, the differential of the big adjoint I of x is equal to little add x. So let's see here. And I think that's not immediately obvious. We're going to prove it here. The derivative with respect to time, 0. So I look at the big adjoint of e to the tx acting on y, but that's you conjugate by this guy, right? And then product rule and evaluate at 0. That gives me xy minus yx, which is little add x of y. So this, on the other hand, was the differential of the adjoint of x, differential of the adjoint at I of x, all of that acting on y. So this shows that this is equal to that acting on y on both sides for arbitrary y. So consequently, this equality is true. All right. So we have that the adjoint goes from G to that. It's a smooth homomorphism, and it can be showed by the reader. See exercise 7.15. Any such homomorphism sends one-parameter groups to one-parameter groups. Thus, it's determined by its derivative at the identity. So consequently, the adjoint of e to the x is equal to e to the differential of the adjoint of I at x, which is that. Cool. Alrighty. Here I have told us to look at page 120 to 121 of Tapp. Why is that interesting? Curious. Oh, so here he has a really nice explicit example of the adjoint action of SO3, and it's really interesting. In this, with his choice of basis and everything, he has that the adjoint big add actually puts SO3, big SO3, into GL3 just by the inclusion. So he finds a basis such that the group is represented by itself, which is kind of cool. But anyway, of course there's much more in chapter 8. I don't know how much I'm getting across to you guys here with all this, but keep trying. So moving along here. Oh, seems like a good time to start